Okay. All right, just take it away. Without further ado.
Okay, and this is about my lowest volume, so yeah, if you can't hear me, I can definitely dial it up. Okay, so, well, first of all, thank you, JP, Nick, and Efren for organizing such an awesome workshop and school. I'm really happy to be a part of it. And thank you, Bianca, for an awesome talk about high-pressure neutron, which I feel like, as well, I'll talk about later, I have kind of categorized experiments into easy and hard high-pressure work, and I would put that all under hard, at least in my book. So yeah, it's really a pleasure to talk to you today. So my background is in also kind of materials synthesis and looking at structure property relationships. And so I sort of just also fell into doing high pressure work as a tool to, yeah, understand structure property relationships. And so that's what I'd like to talk to you about today. But what I found over the years is how esoteric and specific high pressure work is, where a lot of it is creativity of troubleshooting this very unique little problem and maybe bringing in a tool or a technique that's kind of just completely from some other field. And so my hope is to make this as practical as possible about all the little kind of tricks of the trade and things that you might run into in a high pressure experiment. So first, first we've got to get started.
Down arrow. We have to click on these.
There we go. I think I just needed to click on. Yeah. Okay. So first, before I get started, I would like to thank my group. I have a fantastic group that I have a lot of fun with, and they're a great bunch of graduate and undergraduate students. In particular, Lakna and Raul are the two that do high pressure work in my lab, and so they are also even collaborating with Bianca in a very lovely collaboration we've started up, so I'd like to thank Bianca. But also all of our other collaborators really make science is such a team effort. Also funding agencies and the University of Notre Dame. Okay, so just also to give a little background of how I got into this and why I care about high pressure, I'll just motivate this all by saying that I'm a hybrid materials chemist. So I've really I love solid state chemistry and have seen lots of wonderful posters and science already. I like to kind of add together solid state materials and some of the benefits that molecules can provide. And so I don't think I have to motivate why solid state materials are important, in particular for energy related applications and information storage. And that all stems from the fact that they are stable, but maybe more importantly have this extended electronic structure that of course even gives rise to all of the long range order phenomena and quantum properties that we are talking about in this workshop. But I would argue that they are pretty energy intensive to synthesize most of the time, especially if we're doing high temperature furnace-based syntheses. And they are relatively challenging to tune, at least relative to, for example, the degree of exquisite control that molecular chemists have. So organic and organometallic chemists, can dial in very specific atoms and architectures and stereochemistries into pretty complex molecules at this point. And they're maybe easier to process in terms of energy, but of course, they often lack the lower durability that extended solids have, and by definition, being isolated species don't have extended electronic structures. So as a hybrid material chemist, I really like the idea of kind of combining some of the strengths from these and trying to avoid the downsides. So my group develops a lot of different hybrid material platforms. And one major one we're trying to develop, which I think is hopefully a little bit relevant for this workshop, we're calling hybrid bronzes. So many of you might be familiar with metal oxide bronzes. These are mixed valence metal oxides like tungsten or molybdenum or niobium or vanadium. And when they're reduced, they have this high concentration of pretty free electrons. That high concentration of electrons reflects light, and that's why somebody decided to call them bronzes, because they're shiny. And that's the only resemblance to bronze alloy. But these have really, really interesting properties. The inorganic compounds are anywhere from insulators to semiconductors to metallic to superconductors. There's charge density wave behavior. Some of them have really exotic spin states. So they're really interesting materials, and we would like to add in additional functionality and handles to tune, especially in the synthesis. So we're making hybrid organic inorganic metal oxides. We can actually synthesize these in water near room temperature. They're air and water stable. but they have really interesting conductivity and optical properties. And so we're excited to build those towards future applications. But understanding the structure property relationships is really important, and so we've been putting them under pressure as well. And so I'm really sad I'm not going to be able to be here for the research talk, so I thought I'd have just a couple slides on that. And so here I'm just showing us tracking the interlayer spacing between our metal oxide layers as a function of pressure. And depending on the architecture at the molecular level of these materials, bilayer ones, where there is no direct bond between the layers and you just have a van der Waals gap between these organic molecules, we get a more or less monotonic decrease in the interlayer spacing. But with materials where we have a pillaring ligand, such as 4,4' bipyridine, we then get this weird turnaround in our interlayer spacing, this sort of negative compressibility of that interlayer spacing. I'm not just saying this is fairly negative compressibility. And so we're really excited to understand questions like that, of why that is, what's happening there, and all sorts of other interesting high pressure questions. And just briefly, we also have projects on then using molecular tools, molecular synthetic tools, to either synthesize or modify solid state materials. So using molecules that have internal driving forces to do so. But I won't focus on that today. Okay, so, I think I guess a little bit happy to not see a very similar slide to this. I'm sure many of you have seen this as a motivating way that people talk about pressure. But it is really impressive to me, the sheer scope of pressure in the known universe, many more orders of magnitude than most other kind of thermodynamic parameters out there. And of course, we're living here at 10 to the 5, but diamond anvil cell techniques get us into this 10 to the 9 to 10 to the 11 regime, where we're really able to tune interatomic distances, solid state structures, orbital overlap, all sorts of interesting properties. We can also induce chemical reactions, so make new phases, and of course, relevant for what we're talking about in this workshop, magnetic and electronic transitions. And really what we're doing is this simultaneous modulation of structure and property, and the diamonds allow us to then look at the material properties when we're doing that. And so it's this really powerful tool. I would also argue that it allows us to really probe model systems, as well as, of course, ones that are applicable to energy-related applications or information storage. Okay, so the diamond anvil cell, a lot of this is going to be kind of going way back to basics. And so I'd like to really just go through all of the different parts of a diamond anvil cell, because each one can be swapped out and therefore designed for your given experiment. So diamond anvil cell, of course, leverages a high force per unit area. And so the important bit is in here. This is our sample chamber, housed by the diamond culettes, the faces of the diamonds, as well as some gasket material. But even though we're applying uniaxial force, of course, we're compressing the sample medium, or the sample itself, from hopefully all directions, so isotropically. And so choice of that sample, the pressure medium, is also very important. We might put a ruby in there for measuring pressure, but then ultimately, as I mentioned, diamond anvil cells come in many different shapes and sizes, ones that you can put into a PPMS or MPMS or a squid, and ones that have a really wide opening angle, great for single crystal diffraction, kind of everything in between. So of course I won't have time to cover most diamond anvil cells today. I thought I would focus on maybe what is, in my mind at least, the most standard diamond anvil cell, which we often just call a symmetric cell, and go from there. And so the real key here, though, is that the diamonds are transparent to this wide range of radiation. So here are just a few of the experiments, spectroscopy or diffraction, that you can do in a diamond anvil cell. And you are doing this in theory, especially if you're controlling temperature over a really wide temperature pressure phase space. Okay, so inside a diamond anvil cell, here's a really nice cutout showing all of the different components. So this kind of where our sample sits is right at the center there. So very small, usually the diamond culettes are on the order of, somewhere between 100 and 600 microns in diameter. The back of the diamond is called the table, so that's right here. And of course, the diamond shape and how it's cut in particular will dictate your maximum pressure, in addition to what the culet size is, just as a function of, is the diamond going to survive? Is it going to be strong enough? But those diamonds are then mounted on seats, which have a little hole in the back that opens towards this conical opening, and that conical opening that's part of both the diamond anvil cell itself, but also the seat really also dictates, for example, what range in 2 theta or scattering vector you can access. And so then choice of seat becomes very important. And so we mount the diamonds on these seats. We make sure they're really, really well aligned. Bianca spoke to the importance of diamond alignment, and I'll talk about that later. That really also limits what your maximum achievable pressure is. Those seats are then mounted in different parts of the diamond anvil cell. And so in a symmetric cell, we call it symmetric just because the distance from the bottom to these diamonds, from the top down, is the same. But the symmetric cell has two parts. One I would call the piston, which I traced it out with my laser there, that we mount one of the diamonds in. And the other part is called the cylinder. So it's the top part. And these fit together really snugly and nicely, and kind of they're perfectly machined, so they always guide the diamonds back into the same spot. Those are then connected with these screws, and that's these screws. Often in a symmetric cell, we have left-handed and right-handed screws. That's just sort of an engineering way to hopefully make sure that you're compressing evenly on all kind of different parts of the diamond anvil cell so that you don't get tilting of your diamonds, even on a very, very microscopic level. But it's actually not the turning of the screws that's really truly imparting the compressive force on your diamonds. It's rather that these screws are compressing washers that are, in fact, springs, these Belleville springs. So they're curved. And so when you turn the screw, it compresses those springs, and that's what then dictates what force you're imparting on your diamonds. And so then choice of what the spring constant of those washers is, but as well as how many of them and in what configuration we put is really important. And you want to keep track of that. So keeping track of all of these different parameters in your experiment is really important for reproducibility. And then finally, I'll also just mention set screws. That's maybe our very first practical note. So a set screw is in there really just to prevent uncontrolled compression of the two diamonds. So if I tighten these screws, then my diamonds are squeezing together, and unless I kind of provide a counterbalancing force, it'll eventually equilibrate, but that might take a very long time, especially if you're relying on kind of displacement of gasket metal. And so it might be nice to compress it a bit and then put your set screw up to really lock in place that exact pressure. So the set screw can be really important for even preventing your diamonds from breaking, but it can also be one of the very first things that might go wrong in an experiment. You forget to take off the set screw, you keep tightening and tightening and tightening. Why isn't my pressure going up? Oh, the set screw is up. So I'll try to give lots of little practical things of what might go wrong in your experiment. Okay, so let's focus in on each of these different little parts of our diamond anvil cell. So we've got the diamond anvils themselves with the culet, which again dictates the maximum achievable pressure. I think I have to go along that too much, but generally I would say these numbers here of 15 and 55 gigapascals, those are very practical numbers of taking all other parts of your diamond anvil cell into consideration. Roughly that's about what I would hope to achieve in a good experiment. Okay, you can even of course get much higher pressures in diamond anvil cells depending on how those tips are cut and machined and shaped. And that's, when you see all the work done on, for instance, metallic hydrogen, people achieve it with very specialized diamond anvils. But I would also like to focus on the fact that depending on the measurements you want to do, the type of diamond really matters. So there are, of course, both natural and synthetic diamonds, and each have their merits. These are the general types of diamond overall that really just dictate, or really just speak to what impurities there are in these diamonds. So for example, in type 1 diamonds, nitrogen impurities are the primary impurity, and types 1A and B are about how those nitrogen atoms are clustering. And then type 2 have very few nitrogen impurities, but they can have boron impurities that are even semiconducting diamonds, so you might not necessarily want to use that for a conductivity measurement. Overall, what I would say is I think I would recommend, if possible, for your diamond anvil cells, try to go with type 2A. And the reason for that is it's only marginally more expensive than some of the other types, but it has such low impurity concentration that it has very low fluorescence. And so either in UV vis or some type of absorption spectroscopy measurements or photoluminescence or even X-ray measurements, diamond fluorescence can play a role. And so you might even see this by just seeing sort of some blue glow of your diamond in an X-ray beam or in a high energy laser. So keep an eye out for that. Okay, so next we attach our diamonds to seats, and the way we attach them matters, so I'll get to that in a moment, but the choice of seat material also matters. Remember I said that the opening angle can help dictate the range of 2 theta or scattering vector that we're achieving. And so often people go with tungsten carbide because it's a very robust, hard material, cheap, easily machined, and we can have a very large opening angle. But of course, tungsten carbide does scatter X-rays or your beam very strongly, and so then you hit kind of a hard limit when you get out to the outer range of that conical opening. And so if you wanted to especially do, for instance, an X-ray scattering measurement through a traditional axial geometry experiment where you're shooting X-rays kind of through your top diamond, through the sample, through the bottom diamond, and out the back, you might want to go with something like cubic boron nitride, which is more expensive and brittle, so it has a smaller opening angle, so therefore not maybe necessarily as good for a photoluminescence or UV vis experiment, but it's close to X-ray transparent, and so you'll have very low background. So you can even mix and match. You could have tungsten carbide on one side and cubic boron nitride on another in your diamond anvil cell. Okay, so mounting the diamonds, I think gets you a large percentage of the way towards then having very well-aligned diamonds. And traditionally, there are kind of 2 different ways. The force fitting in a metal ring is really, just pressing the diamond into a ring, and then it's pretty permanently in there. And so some companies, like I think Easy Lab was mentioned before, do this, and you can just purchase the diamond as is. And then the setup is pretty minimal for that, and it's a pretty robust system, so your diamond's not going to come out, and it's reproducible. But I would say it's less modular and tunable. The other, I guess, kind of very traditional way that people put diamonds on seats is using epoxy. And so that allows you a lot more freedom, but it can be a little finicky. So the pros are, you can easily swap out all of your different components, so it's very modular. But the epoxy can come unstuck if you're going through big temperature swings or there's solvent present, or if your diamonds are not well aligned. And so overall, I just wanted to, it's good that we are giving out these slides. Hopefully some of the little practical notes here, if you're doing diamond anvil cell experiments, will actually be of use. And so I really like using this particular epoxy with this particular curing catalyst, just because it's a really robust epoxy that has a very low coefficient of thermal expansion, really resistant to solvent, it's electronically insulating, so it works pretty well. Okay, so I found this video, so thanks to Easy Lab, and I sped it up and just showed the gluing part. But as I mentioned, alignment is really important. So with this jig, you take a seat, put it in, and put your diamond on top. And then it's subtle, but these screws are turning here. And what you're doing there is you're sliding the seat relative to the diamond to get it really, really well aligned. Then finally, once you're satisfied, you put a little bit of epoxy around the base, and you're done. And so that took, 20 seconds. In reality, I would spend hours doing this because then you'll get a really well-aligned diamond on your seat, and that'll make the rest of your life much easier. So yeah, that definitely takes a lot of practice, but it kind of almost illustrates for that and diamond anvil alignment itself, you have to have a lot of patience, and it's all of this fine little tweaking of screws to get the diamond perfectly aligned. Okay, so speaking of aligning diamonds, the reason you really want to do this, and this is honestly, if you do start doing high pressure work in kind of a traditional high pressure lab, this is probably what they'll have you start doing. Because the first thing you want is well-aligned diamonds and to understand how a diamond anvil cell works. And so you'll practice aligning diamonds. And so this raises the maximum achievable pressure really by preventing the possibility of your gasket failing, essentially rupturing along one direction. And also the diamonds are less likely to break. It allows you to center your sample chamber more easily. So I'll get to this in a moment, but to make the sample chamber in your gasket, you're drilling a little hole. If your diamonds are not aligned, that hole will be sort of angled through your gasket and you won't have as good of a sample chamber. So all sorts of good reasons to do this. And so this is a diamond anvil cell that I aligned myself. And so you can just see by looking like the tips, or the edges of the culettes are really well aligned with each other, but I'm not showing you the whole picture here. You should take my word for it that this is aligned, but actually, if we wanted to really know that this is aligned, we would have to do a lot of different angles, look at it from a lot of different ways. So the way I typically would do this is consider 4 different positions. So I've tried to schematically draw this here and keep track of these red dots. So I literally with a Sharpie would mark the 2 different halves of my diamond anvil cell, my piston and my cylinder, with this sort of 12 o'clock mark to keep track of the orientation of the diamonds relative to each other. So if this is our home position, it's then nice to be able to compare that home position to one in which we've turned both parts of the diamond anvil cell 90 degrees. So that's looking, from X and Y axes, if you want to think of it that way. Then in C here, we're back to the original position for our for our piston, but we've turned our cylinder 180 degrees. And likewise here for D, again, our piston is in the same position as B, but our cylinder is turned 180 degrees. So these four positions allow you to determine the alignment and the kind of rotation axes of these diamonds. So I just really quickly, and I won't go through this super in detail, but the way that I would think about then aligning it is take your time and draw everything out. The way I like to think of it is there being a little line running directly down the axis from table to culet in a diamond. And we want those lines from all views in A, B, C, and D to be well aligned. And so as long as you just on a little post-it note are drawing out where are your lines in each of these different orientations that you're looking under a microscope, you'll hopefully be able to keep track of everything, because otherwise you're sort of going to get lost. So for example, let's say I'm looking at positions A and C, shown right here. So the only difference between these is that I'm turning the orientation of my cylinder, so rotating that top diamond by 180 degrees. And so if I see, here's my piston diamond and here's my cylinder diamond, and I see that it rotates up to this position when I turn that cylinder, well, now I know if I'm starting from position A, I need to move that diamond up a little bit. So I turn a tiny little screw. And so I've got lots of examples there, but of course I won't go through those. It takes a really long time. You can even spend, a whole day doing this, but I would argue that it's worth it to do that. Okay. Diamond anvil cell work is really fine and precise, and you want to have a nice, really ergonomic workstation. You've got everything ready in order to prepare your diamond anvil cell. And so I just wanted to briefly cover all of the little kind of tools. Some of these are very cheap and it might seem trivial, right? I've got Q-tips on there, but the right Q-tip matters. And so all of these are such funny little things, but I thought it would be nice to cover some of that. So definitely, first and foremost, it's really great to have a high magnification microscope. It also has a really long working distance. You've got your hands under there and you're doing very fine manipulations. You want to be able to see it well, but also have plenty of space. You need the right set of Allen keys, and so I just wanted to throw on there the kind of standard Allen keys that you might be using in a symmetric cell, but of course that's going to depend on your cell architecture. One big thing that different high pressure people have their own preferences, but for manipulating actual samples, people often use some sort of needle or sometimes a capillary. And so I like to use a tungsten needle. It's very robust. You can resharpen it easily, but it allows you to manipulate really fine samples on the sub 10 micron scale quite easily. And then also getting some good needle nose tweezers. And then of course things that cut, toothpicks that can manipulate things but not scratch because they're metal. You can even sharpen them with a razor blade. Lots of plastic baggies for all of your tiny, tiny, tiny little parts of your DACs. Solvents for cleaning. WD-40, because I feel like we need that all in our lives for just pretty much everything, and sandpaper for sharpening or polishing things. And so that's kind of, most of this is portable. You can even have a little kit with you that you take and is mobile. Take your small diamond anvil cell and you're ready to go. Okay, so one of the next important aspects of diamond anvil cell work is the gasket choice. And of course, Bianca mentioned some for neutron measurements. The main ones that I'm used to using, and especially for spectroscopies or X-ray diffraction, would be either steel, tungsten, or beryllium. So steel, of course, very, very cheap. From McMaster or Granger, you can buy just a sheet that's about 250 microns thick, and then punch out discs of it, and then you have essentially gaskets for life. But even though it's cheap, I would keep in mind steel does undergo a phase transition around 13 gigapascals, and it might not necessarily be compatible with all other components in your cell. It might also be just that you want to achieve a higher maximum pressure, so you might want something a little more robust like rhenium or tungsten, but of course those are quite expensive. And then finally, if you're doing, rather than an axial measurement, where you're sort of going in the back of the diamond and out through the other end, if instead you're coming in from the side, you might want to, for like an X-ray absorption spectroscopy measurement, your gasket itself has to be as X-ray transparent as possible. So people use beryllium, but of course then you have to worry about the toxicity of beryllium. Okay, so that's a gasket looking from the top down. Notice I've even kept up with my 12 o'clock little notation there. I like to keep track of where the gasket is in the diamond anvil cell, so I make a little scratch, and that I know then where that is relative to the outer part of the diamond anvil cell. Okay, so when you then put the gasket into the diamond anvil cell, even the supports matter. So obviously the tip of your diamond is very small, and if you just put the gasket in, it could easily tip around. And again, then if you've, on the macroscopic scale, tipped it, then if you drill a hole or in general are trying to achieve a high pressure, it might be more likely to fail. So you want to support it well so that it's nice and level. And so typically I actually use modeling clay, and you make little tiny balls, for instance, on which the gasket can rest, and that usually works pretty well. But watch out for things like the fact that modeling clay on a microscopic level has all of this oil that comes off of it. And so if you get that too close to the tip of your diamond, then you'll have a dirty diamond, and kind of it won't be as likely to give you good results. You might even see some weird peaks in a measurement. People also do use beeswax, and that's a little more kind of stiff and supportive, but sometimes actually sticky is bad. So on the very microscopic scale, when you're manipulating things for diamond anvil cells, things tend to stick, and it's not, there's, it can be more difficult to manipulate, and so that can be a downside to using wax, but certainly people can use that as a more stiff support. Okay, one of the really big advancements in early diamond anvil cell or pressure cell work was the idea of pre-indenting gaskets. And the reason for this is when you think about when you're pressing these diamond tips into your gasket material, I told you, for instance, the steel foil that I buy is 250 microns. But in actuality, we want our sample chamber to maybe be on more something like 20 to 50 microns in thickness. And so that's a lot of steel to displace when you sort of are pressing with those diamonds going from here to here. And so if you do that ahead of time, it's much more likely that then your sample chamber and everything about it will stay in place when you're doing your actual pressure experiment. And so that pre-indentation, it thins the gasket material, but it also, after you've pre-indented it, or you're doing all sorts of taking apart and putting your cell back together, you want the diamonds to be guided right back into the exact same spot. And so when we pre-indent, the facets of the diamond create, nice facets on the indentation, and that guides the diamonds right back into the exact same position. So pre-indentation also gets past any sort of phase transitions in your material. So I mentioned steel, and I'll have that on the next slide. And that so then kind of allows you to, if those phase transitions are irreversible, avoid them also complicating your experiment. In general, this is my rule of thumb. Typically go to at least half of the final target pressure of your actual experiment. So let's say I want to go up to 50 gigapascals in my experiment. I'd aim for pre-indenting to at least 25 or so gigapascals. Of course, as well as going past any irreversible phase transitions. So you would typically then, after pre-indenting, measure your gasket thickness. You can do that using a micrometer, but I have a fun other way to do that in a later slide. And then here I just wanted to show you a very practical pre-indentation of steel, where you can even visually see the phase transition of steel. So here I'm zoomed in on steel gasket. This schmutz here is actually a crushed ruby, and so that's a really sort of rough way of measuring pressure. That ruby is obviously not in a very hydrostatic or a very isotropic environment, but it gives us a rough idea of what the pressure is. But you can see all of these grains in this alpha steel, that once it goes past about 13 gigapascals, those get really wavy and almost disappear, and you get this really shiny surface. And that's telling you that your steel went through this phase transition. And so don't freak out if when you're pre-indenting and you're measuring this ruby fluorescence, you hit about in the region of like 9 to 10 gigapascals, and then all of a sudden, oh, my pressure isn't really going up at all. Why is that not happening? And that's because, well, first we're still displacing a lot of metal, but we also need to go through this phase transition completely before we really register a continued increase in pressure. Right, then, after we've pre-indented, we need to create our sample chamber, and so we need to drill it. And there are two main different ways that people drill. sample chamber in a gasket. One is using a laser, and that's really precise and nice, and you can dial in exactly where it is and align it really well. But laser drilling apparatuses are pretty expensive, and not everybody has them. A cheaper and kind of more versatile option is these electric discharge machines. And so different companies sell these, but it operates by just having a really fine, maybe like 50 to 100 micron diameter drill bit, which is really just a wire, and you're passing a whole bunch of electric discharge through it that then drills through your gasket when you put them in contact. So what's really nice is it drills a nice electrical hole and then immediately stops the minute it's out of electrical contact once it's finished drilling. And so you can choose the diameter of your drill bit by just swapping that out quite easily, and that dictates the size of your sample chamber. But of course, it's a little finicky, and so playing around with how you do that and align it is really important. Okay, so for drilling, what you want to look for is a really well-aligned sample chamber. And what you want is a good thickness of gasket. So if we're looking, this is just sort of on the pre-indented part of the gasket that was touching the Q-lip. And so we want a good thickness of gasket to prevent rupture. So when we're going up to high pressure, we don't want a thinner area here. That would be the most likely place where that gasket might rupture. So we both want it well aligned and also to have a good appreciable thickness here. So for example, for maybe a 300 micron gasket, I might want to drill a 100 micron hole so that I have 100 microns all the way around, and that's certainly plenty more than enough. You can go down to an ideal X value of even lower. I'd say probably no less than 50 microns here or so. Rough rule of thumb. Okay, so another really fun way, though, that you can really accurately measure the thickness of your gasket is by using interference fringes. So I always like coming up with kind of really kind of tricks of the trade here. So if you drill your gasket, you now have just empty space. And if you enclose that empty space with your two diamonds, well, now we have, if it's on the order of 20 to 50 microns across, really nice flat surfaces that give beautiful interference fringes if you shine light through it. And so then you can just use those interference fringes and these equations here to really precisely determine the thickness of your gasket. And that's even a trick you could use if your sample itself is transparent or translucent and you want to monitor the thickness of your sample throughout a pressure experiment, for example. Maybe you care about conductivity and therefore you need to know what the thickness of your kind of sample pellet is or something like that. This would be a method to do that all throughout your experiment. Okay, so I will just say implying even force is really, really important. And so it might sound stupid, but I even always make sure to not turn in different order. I always kind of go from one side to the other in a crisscross fashion when I'm turning my screws, just to apply pressure as evenly as possible. I think diamond anvil cell work is great for people who are very neurotic because you keep track of all of these tiny little details. And so when you're compressing, just keep an eye on the shape of your gasket hole. Take a picture of it before your experiment, see what shape it is, and keep an eye on it. It's going to shrink over time as your pressure goes up. You're displacing more gasket material, and that'll shrink. But you don't want to see it bowing outwards into some kind of oval shape like that. If you see that, don't freak out, but I would just say maybe stop going up in pressure and very carefully, slowly back it down in pressure. That'll prevent you from breaking your diamonds or something like that. Okay, to measuring pressure. So you saw that little ruby sphere that I had smashed on the steel earlier. So the reason we use ruby is ruby fluorescence shifts predictably as a function of pressure. It's these really nice sharp peaks in purple that I'm showing at ambient pressure that shift towards longer wavelengths as you go up in pressure. And this is actually, you can see it's broadening quite a bit here. This was in a scenario where I wasn't using a pressure medium, and so there's a little bit of strain on that ruby, and you'll see some broadening. But those peaks you can easily fit, especially a lot of programs fit that very easily. And if you literally search Ruby pressure calculator and look it up online, you will find nice tools that reference these papers and the measurements they did to track how the fluorescence should shift as a function of pressure in either hydrostatic or non-hydrostatic environments. So yeah, it's a really robust way, especially because one of the experiments that a lot of people do in high pressure very routinely is on spectroscopy. And so Raman's often use, a 532 laser or a 633 laser, and that will excite the ruby. So you can measure your pressure and then just move over onto your sample and measure a Raman spectrum. I would note that just keep an eye out. Don't quote too many significant figures on your pressure in these experiments. No matter what the pressure calibrant is, there is an error on that pressure. And so, don't quote 5 significant figures if the error is something like 5%. And then finally, it's great to measure the pressure before and after your experiment. High pressure measurements, the hope is that this is more or less in the thermodynamic regime, right? We tighten our screws and hope that our sample has equilibrated to a given pressure. But in actuality, you might be limited by how much beam time you have or something like that. So you want to let it equilibrate to a pretty decent amount, but measure your pressure before and after, and that'll give you almost an error bar as well on the pressure of whatever spectroscopy or diffraction pattern you took. You can do it in other ways as well. You can measure pressure in other ways as well. I don't really have time to focus too much on this, but of course you can include a diffraction standard, something like platinum or copper metal. And those equations of state are well known, and therefore you fit exactly where those peaks are and figure out what the pressure in your sample is. You can even use sometimes alkali halides. There can be issues with those in terms of, for instance, potassium bromide also has a phase transition between about 2 and 3 gigapascals. But it has very sharp, nice peaks, and its behavior under pressure is very well known. And you might want to use that because it's transparent, so good for some spectroscopies. Actually, though, one other kind of very rough way you might be able to tell pressure as well is by tracking the Raman peak of diamond. So diamond has a really strong Raman peak, and it'll shift because your diamonds are under strain. And so you could imagine making some sort of calibration curve with that. It's of course not going to be exactly what the pressure is for your sample itself because it's the strain that's on the diamond, but you could imagine making a rough calibration curve there too. All the trick of the trade. Okay, so next, pressure media. And so when choosing the pressure medium, what's really important is the fact that all media will become a solid at some pressure, and depending on the behavior of that solid, it is no longer going to be hydrostatic, meaning it's no longer going to isotropically compress your sample when you're reducing the sample chamber volume. And that's going to cause broadening in peaks, or even depending on if you have a really fine probe at a very small spot size, different spots on your sample might give you a different diffraction pattern or different spectrum. And so keeping in mind what your medium is and how that might affect your measurement is very important. You also want to think about, will it react with my sample? Is it easy to load? That's not always trivial, and many other factors as well. So some of the pressure media out there are things like gases even. You can pressurize the sample chamber with various different gases, silicone oil, methanol, ethanol mixtures, and even some solids that are soft, maybe alkali halides. So the way people originally determined what the pressure, the hydrostatic limits were for these pressure media were a couple different ways. Klotz and co. did ruby fluorescence by just essentially putting different rubies across different spots in their sample chamber, and then looking at the fluorescence at those different spots. And so if you have a distribution of pressures, you know that your pressure medium itself is not hydrostatic. And actually, I would keep that in mind because you can easily load multiple ruby spheres in your sample when you're doing a diamond ample cell measurement itself, and then keep track of, is my sample experiencing uniform pressure across the pressure cell? People have also done things like interferometry to also figure out hydrostatic limits. So this is what some of those data look like. This is from Klotz's paper. And so you can see essentially just the standard deviation of that ruby fluorescence. And you can see it really takes off at various different points for silicone oil. There are methanol, ethanol mixtures. So methanol, ethanol mixtures, or even with some water in there, have pretty good hydrostatic limits, but then it really rapidly deviates. And so, it's good for that low pressure regime, but then afterwards, maybe not so good. Some of the inert gases are really quite good. Helium, of course, is really, really good. Although, fun fact, helium embrittles diamonds because at high pressure it can intercalate into diamond. So if you've done a lot of helium loading measurements over time, eventually those diamonds might be more brittle. Okay, so, there that is, yeah. So some of these, like oils, they're very easy to load, they're not volatile, and things won't move around as much, but they're not as hydrostatic. So it's really kind of just a balancing act. Yeah, I would say I do like using alkali halides sometimes because they can act as a transparent material and therefore maybe works for spectroscopy. It can be a diffraction standard, and they're pretty soft. But you, of course, would just have to keep in mind how soft, how compressible is the material that you're measuring itself. Okay. Right, so sample loading, yeah.
The noble gases, you're loading those as a gas.
Yeah, so often you'll put your diamond Anvil cell in a much larger pressure chamber, but the diamond Anvil cell is like the diamonds are a little bit apart. You pressurize the whole sample chamber and then use a driving mechanism to then close the diamond Anvil cell while it's pressurized and then seal in that. But actually some people, even if it's, for instance, nitrogen, you can actually just dunk your diamond Anvil cell in liquid nitrogen and close it, although that can be kind of like a little tricky and cumbersome, not so fun, but yeah.
Right, and the pressure is high enough that once...
Yeah, so some of those gas loading apparatuses, you pressurize it to maybe 0.2 gigapascals or something like that, and so yeah, that's enough to then not have it be too compressible and not have your just sample chamber shrink to nothing. Yeah. Okay, so loading is a real challenge, but really important. So first, you would ensure you have all the right configuration, and then take time cleaning off your diamonds. So this is what a dirty diamond looks like, and it's got all of that stuff on there that might be from your Q-tip or something like that. So it takes practice to do just one clean swipe of a Q-tip and then get it to something where the face is nice and clean. Then what you're really doing is loading in sample bit by bit with a needle tip. And so that takes time, and maybe don't drink too much coffee. Maybe we'd all be good at it right now. You essentially add it in bit by bit into your sample chamber, and then you're repetitively opening and closing your diamond Anvil cell and kind of gently squeezing that sample into the sample chamber so that it fills it nicely. But you don't want to add too much pressure before you've actually started your experiment. And then finally, you'll place a ruby sphere maybe on the top diamond, but keep track of exactly where it is so that when you close it, you know where to find it, because that's not always so easy, especially the ruby sphere is pretty light or transparent in color, and maybe relative to a dark sample, it'd be hard to find. So here, for example, is a ruby in a translucent sample, so this is backlit from behind, and so you can see that's where I would hit it with my laser to measure pressure. Okay, so finally, in the last little bit here, I just want to talk about some of the measurements that you might do in diamond Anvil cells and some of the pitfalls. And this is how I divide them into those kind of maybe more normal and maybe more tricky experiments. So Raman spectroscopy and photoluminescence and powder diffraction are much more standard, and once you get the hang of diamond Anvil cell loading, they're not too bad. These ones are a little trickier. Okay, so Raman spectroscopy, a lot of people, you do this because what you're really doing is you're probing vibrations and bonds. It's a vibrational spectroscopy that also gives you symmetry information. So these are symmetry labels for these different peaks. So depending on even orientation of crystal, you'll get different peaks show up or not because of the symmetry that's present. But you will expect to see Raman peaks shift generally to higher Raman shift with increasing compression because your lattice is stiffening. But this is a really sensitive probe of bonding, phonons, all sorts of interesting things going on in your sample. And so here's some just measurements I took on this layered chromium trihalide material. You can even see some beautiful color changes. And it's a good way to look for things like phase transitions. So note how these two peaks here, this A1G and EG, merge together up at about 9.5 gigapascals. So it's a really great way, and so many institutions just have a Raman, confocal Raman microscope available. So that's a great way to kind of not have to go to a beam line. So just some practical notes here, things like consider laser power, and that you might, can this go out? Can everyone still hear me? Okay, so keep in mind laser power, and that you just don't want to blast your sample, so start small and go up, and keep in mind that even though you think the laser power might be low, it's a confocal measurement, so you're focusing it down, so what actually matters is irradiance, power per unit area. Okay, and then measuring different spots, checking for is it the same everywhere, as well as waiting for your pressure to equilibrate are really important. Photoluminescence spectroscopy, I put this in under easy because if your sample is excited by the laser on the Raman, like if its band gap or its photoluminescent transition is of the right energy, it's really easy to also measure photoluminescence on a Raman spectrometer.
So here's an example of methylammonium lead iodide, which has a direct band gap and it's very photoluminescent, where you can track how that photoluminescence and actually therefore the band gap evolves with pressure. And here I'm just tracking this as the peak position as a function of pressure. So, again, keep in mind things like photoinduced reactivity or laser damage, and measure your different spots. And keep in mind your radiative mechanism. So photoluminescence, of course, depends on so many things, and there's so many non-radiative mechanisms out there that might quench your photoluminescence. So don't get disheartened if you lose it, but all sorts of different changes do happen under pressure. And then finally, I won't spend too much time on diffraction because others are covering that a lot, but diffraction is really a bread and butter technique for determining structure of materials under pressure. And in kind of its simplest sense, you just put your diamond anvil cell on a goniometer and then measure a transmission measurement and collect nice Weishauer rings on a big 2D detector. So it's overall generally not too difficult, and a lot of the beamlines at like ALS or APS have really nice automated systems now for even incrementing the pressure, measuring the pressure online, like rather than having to take your diamond anvil cell off. So those facilities are really great. But it allows you to track all sorts of different things like appearance or disappearance of peaks, phase transitions. Here you can see this material even like under kind of partial amorphization. One thing to watch out for is that you might sometimes get spotty Weishauer rings. If you have fairly large crystallites, and because your sample is literally nanograms, you're not actually sampling that many different crystallites, and you have a very focused beam. So you might get very spotty diffraction patterns because you're only looking at a few different crystallites. And so you might do something. Okay, so here's some kind of spotty but decent looking diffraction rings. And then analyzing this data takes a little bit of just making sure you're doing everything right. So you want to calibrate it well using a diffraction standard to know your sample to detector distance and all of the wavelength and all sorts of aspects of your specific diffractometer and setup at the beamline. You also want to consider things like your X-ray wavelength and avoid absorption edges. If you have the ability to tune it, that's great if you're in a synchrotron. And so you might want to go to pretty hard X-rays, but avoiding an absorption edge. Hard X-rays will allow the X-rays to not maybe be absorbed as much or to allow you to access a very wide range of tooth data. Okay, so then masking is really, really important, and you have to mask out things like diamond reflections, maybe you have some gasket peaks in there, your beam stop, dead pixels, cosmic rays, and so what I'm getting to here is that if you really want to do a refinement of the data, intensities really matter, and so make sure you're masking very, very carefully. So I would also just say, always check against your expected pattern. Don't immediately say, I've made a new phase and it's really, really exciting. Is it iron? Is it tungsten carbide? Is it your pressure medium? There's so many. Is it aluminum oxide? In other words, your ruby? There are many things that it could be, so always check your patterns against some of those very simple explanations. Okay, so if everything goes right, you can definitely try to extract your lattice parameters, so essentially doing Lebesgue or poly refinement. And then if everything is perfect, maybe try refill. But just be careful because, again, refill is dependent on intensities, and there are all of these things that can be affecting the intensities, so don't overfit. One of the trickiest things, though, is that we often get new phases, a phase transition to a different symmetry, maybe a completely different unit cell. And determining that, especially since pressure can induce very kind of unique unit cells, is very challenging. And I would love to hear if anyone else has better programs than this. What I've used are, this one program, Jade, actually has a very good mechanism for determining unit cells, but it costs a lot of money. GSAS and FullProf usually implement these programs, but they're only just okay. So I'd love to hear if people have other suggestions. Okay, so I really can't cover too much here, but after you have your lattice parameters, then you want to fit the equations of state. So I highly recommend using this EOS fit program, which is free. And so if you have your pressure-volume relationship, you can simply fit that. But again, don't overfit. The more kind of higher order your equation is, of course, the fit itself, the line, might look better. but keep track of your errors on these values. If they're massive, massive errors, it's not a reasonable fit. And so start at the kind of simplest possible, the lowest order equation of state. So here's an example where this is actually a decent fit for a second order equation of state on this material. I got my bulk modulus at ambient pressure as well as my ambient unit cell volume there. But actually what we found is a much better fit if you fit this to two different regimes, like a much, much better fit. And so then what ended up happening, and we kind of fleshed this out with other measurements, was that there is a second order phase transition here where the compressibility really changed at a certain point. We didn't see any appearance or disappearance of peaks or change in symmetry, but things like that can certainly happen under pressure. Okay, and then just finally, I'll end by talking about one difficult measurement, and this is conductivity. I thought this would be a nice way to end, and which is really, really relevant for probably what a lot of you might want to measure. So here are some reasons why all of these things are difficult. In particular, conductivity, just because there's so many extra little delicate things that you have to do. So the issue is that if you want to lie electrical leads on your sample and measure conductivity, the gasket itself, if it's steel or some other metal, is usually conductive. And so you need a way to insulate those electrical leads from the gasket but still contact the sample. So what we do typically is take our gasket and actually drill out almost all of that area there that was touching the culettes. And only have just a little bit left. So if the culet is 300, maybe drill out 290. Then this paper came out and gave a nice way to almost make an insulating gasket that's pretty versatile. It's not the most stable, but it works pretty well. So it's a mixture of cubic boron nitride powder and an epoxy matrix. And so you pre-make this mixture and then just chip off little chunks of it and slowly but surely put little bits into this area, press down the diamond, put more bits in, press down the diamond, keep going and going until it's filled that sample chamber area and all the way gone up the sides of your pre-indentation. The reason for this is, cubic boron nitride is really, really robust and insulating, and so that kind of works well and doesn't sort of break too easily, but also it's sort of moldable because it's in this epoxy matrix. So here's the exact epoxy that I use, and actually we often buy the cubic boron nitride powder from just like abrasives companies. So you won't find it on like Signal Aldrich. Actually, I had a really hard time finding cubic boron nitride powder of kind of the right size and not hexagonal. Okay, so this part is really hard. It takes patience. Putting those little bits in, pressing it down, and not having chunks of it come up with the top diamond when you pull that back off. That happens all the time, and so maybe bring some chocolate along with you to keep your mood up. Okay, then you actually do another pre-indentation. Cubic boron nitride also has a phase transition, and it's pretty cool actually. It becomes pretty translucent, so above around 20-ish in this matrix at least. If you shine light from the bottom, you'll be able to see light coming through. And I'll show, I think, a picture of that in a bit. So beware of that, but then pre-indent to your desired final thickness. Then with your needle tip, you poke out your little sample chamber. So you're almost like drilling with your needle tip and then putting your sample in. So that part is also hard, avoid coffee, but eventually you've got your sample in there. And then finally, you can put something insulating, even Scotch tape on top of this part of the gasket and affix with some epoxy your platinum leads, which are little pizza wedge looking things. I usually like to use 4 or 5 micron thick foil. And while people can also vapor deposit leads on diamonds, I've actually found that to be not as robust. Those leads often, it's easier to sort of scratch them and interrupt electrical contact. They tend to sometimes fail actually, whereas this platinum foil is really pretty robust throughout the pressure experiment. But of course, the sort of depositing the leads is maybe easier in some ways too. Okay, so then you affix those to external copper wires that maybe you coil at the ends so they fit inside the diamond anvil cell when you need to close it. You'll pull them out later. And then finally, the last part is just lots of nudging. So you want your leads to lie down flat on your sample when you put the top diamond down. And so it's a lot of fine adjustments of nudging the leads and the wires around and sort of slowly watching as the diamond is going down to make sure the leads go just perfectly onto your sample. And so they're a little springy, but eventually with that nudging, you'll get them to the right place. Then you'll finally take the top diamond up one more time, put a ruby on, seal it, and then breathe because you're done. Finally, then you'll pull out those, so there are holes on the side of the diamond Anvil cell. You'll pull out those copper leads, connecting them to larger leads maybe, and affix it with some epoxy so they don't get jostled, and then you're good to go. All right, so that's what a final measurement or final setup might look like. This is more or less actually a single crystal that I sort of put in there with my leads onto it in a Vanderpau configuration, 4-point probe, but I've seen people even do more leads for things like Hall measurements. And you can see a little bit of light coming actually through from behind because that's my cubic boron nitride that's past its phase transition. There's light coming from behind. All right, conclusions. Thanks for bearing with me. Oh, yeah.
So, are the leads attached to the sample just by pressure, or?
Yeah, that's the nice thing. And actually, sometimes I worry a lot about my silver paint or my whatever it is reacting with the sample. You don't have to worry about that here, other than just whatever your lead itself is made out of. And there's just so much pressure there that you're actually getting very good contact, and the contact resistance is usually negligible. But regardless, if you're doing a 4-point measurement, you're kind of getting rid of contact resistance anyway. Yeah.
Does the contact make pressure non-uniform, or?
Oh, does contact make it non-uniform?
I mean, the assumption is we have to make a uniform pressure on the sample, and then contact measure the electrical contact resistance display. But I see the contact put on top of sample.
Yeah.
Then the diamond meets the contact first, and then underneath there is sample.
Yeah.
And I'm concerned about the non-uniformness of the pressure on the sample.
You can certainly put multiple rubies at different spots on the sample. I would say that is almost certainly going to be a negligible effect relative to maybe some of the other non-uniformity from just like deviation across your pressure medium if you have one, or things like that. So no, I don't think I would be too concerned about that. The contact itself, it's a really thin, flat piece of foil, and I wouldn't say that's really going to cause much difference in pressure across your sample. Okay, so I'll leave you with these experiments are finicky. Please do actually reach out. I have, as you probably already saw from this presentation, ridiculous amounts of information that's practical that I can give you, and I'm more than happy to, so do reach out. And don't overanalyze your data and always assume that it's an impurity or something went wrong before I got the next big, really cool material phase that's superconducting at 300 degrees Celsius or something. And so I really do love these kind of like creative solutions to high pressure, but even other parts of science. So I actually even have a YouTube channel where we film lab hacks like tricks of the trade and things to get around kind of either cost or knowledge barriers in labs. So please do check that out and send that to me if you have any ideas for us to film. And thank you.
Okay, questions? Thanks for the wonderful tutorial. I have 2 questions. One is, what's the typical size of the diamond side where it meets the sample?
Hewlett? Yeah, so that's typically, depending on what pressure you want to go to, anywhere from 100 to maybe 600 microns in diameter.
The next question is, so you showed how you align the diamond, and then I think it's basically by eyes.
But you can even, like, this is all under a microscope, definitely under a microscope. And with that microscope, literally on the image, there are a lot of microscope software allows you to draw like nice bars and be more quantitative in your measurements. Definitely you should do that as well. But yeah, the human eye actually is really good, especially if you're looking at a very high magnification microscope.
Yep. Yeah, thank you for being very useful. A couple of questions just from my lab to see if it's. So you mentioned for gaskets beryllium. Is beryllium copper particularly worrisome, or is that probably?
Oh, I don't actually know as much about the toxicity of beryllium copper. Maybe Bianca can speak to that, or do you happen to know? Or
They are worried about the beryllium inside the beryllium copper.
yeah,
So it's the beryllium that's
yeah, I
There's
mean-
no concern for the cost as long as it was
Okay.
made after 1949. Prior to 1949, it was made with 2.98% beryllium,
got it.
which forms an oxide, which is really bad for you. You don't want to touch it because you'll carry it with you. You will eventually get it into your bones, and 2 to 3% of the population gets sclerosis and we die. Miserable death. But beryllium, copper, modern day beryllium copper, 1.98%, and there's no worry with that unless you EDM it and atomize and put the beryllium into the air. So pure beryllium is the beast. You have to be careful.
But to follow up, if you use beryllium copper, you'll get none of the benefits of using beryllium because it's mostly copper.
Right.
So it's not going to be extra transparent,
exactly.
so it's not really going to give you.
Yeah, right.
There's almost never a reason to use it as a gasket material.
That's all good to know. Actually, I was more so thinking like, is it particularly brittle, or I guess maybe particularly brittle, or is it a good material to be using for a gasket, or
Using
no, beryllium copper, the modern beryllium copper.
beryllium copper is fine as long as the diamond is greater than 2 million and your Anvil is less than 1 million.
I would always just use steel instead. There's no,
Yeah.
I don't see any benefit that beryllium copper would have. You can get a non-magnetic steel or rhenium or.
I think there are some good reasons to use beryllium copper. And I know several people that
I hate it. So.
I agree with you. And I found that one of the problems was if it's too small, it cracks right in, and your experiment's over at the worst possible time. Everything's gone together, and you're increasing the load, and it's like, oh my God, this is absolutely glorious. And all of a sudden, the gasket breaks in half, and life sucks.
Secondly, for deionization, we typically would go to like 90% of desired pressure. Is there a reason not to do that other than it takes time to do that
The
carefully?
reason I might not want to do that is sometimes actually 90% might get your gasket to be very, very thin. And there are a lot of reasons why you might actually want an appreciable sample volume in there, especially in a diffraction experiment. You don't want a very tiny, small refractive volume. You also never want, depending on what your sample morphology is, it would be not ideal to have it bridging between your two diamonds, because that's a surefire way to not have hydrostatic conditions. And so if you have a very thin sample chamber, depending on if you're especially measuring maybe larger crystallites or even a single crystal, it might be very likely to be bridging then. So yeah, it's kind of a trade-off there where certainly that then would lead you to not have any more of that metal displacement throughout your experiment. It's very well compressed already, but yeah, it might be more of a limitation on the sample side.
And like, so the next one's next.
Maybe you can ask now. You get some more questions.
This was a very nice presentation. So I have a couple of questions. So where do you put the business point, like on the field?
Can you say that again?
Where do you put the ruby? Like for example, when you are doing electrical measurements.
Yeah. Oh, yeah. So, especially for a conductivity measurement, yeah, you wouldn't want to necessarily have the ruby really in there, but you will need to measure pressure. So I might even put one at multiple different spots. And overall, the assumption is no matter what, there's so many non-idealities of this type of conductivity measurement that it's probably not going to affect it all that much. So I might put one a little closer to the center somewhere, then maybe one further out over here, just maybe not too close to the leads themselves. And so what I would do is I would look down at my sample that I've loaded, keep track of where I want the ruby to go. But then on my cylinder, for example, on that diamond, which isn't touching anything, I'll sort of keep in mind where the mirror image should be of where I should put my diamonds, such that when I bring it back down on top, it'll go directly into the correct spot. So you can, take a picture of, when using your microscope, of exactly where you want the rubies to be, and then just sort of nudge them into the exact position they should be.
When we are selecting the basket, we use epoxy recipient. How do you do it, or what do you mix it?
Yeah, so these epoxies, they're pretty liquidy, and actually the correct ratio, it should be a kind of a pretty contiguous chunk that is not crumbly. If it's crumbly, that's probably not going to be a robust gasket. But you also want to kind of maximize the amount of cubic boron nitride possible. So I think we ended up maybe having a 4 or 5 to 1 ratio of cubic boron nitride to epoxy, roughly. But kind of play around with it, maybe make a whole series of them, and whichever one like you can chip off nice contiguous chunks that don't crumble, but that also it's not just all epoxy. That's definitely not what you want. That's kind of the ratio you want.
What size of ruby do you use?
Oh, great question too. So these ruby spheres, I don't know if anyone else has gotten them from anywhere else besides, I get them from Betsa, but maybe some other people make them, but the Betsa ones are really, really nice, great fluorescence. They do have some distribution of size that they come with. Once you buy some from them, it is kind of expensive, but you'll probably never need it again in your life because you get, millions and millions of ruby spheres. And so I usually go for ones maybe on the order of about like 10 microns or a little less across. If it's too big, then you often get a lot of strain across that ruby at higher pressures, or it might even crush, or it might get into your sample measurement. But if it's too small, you might actually even envelop it or lose it in your sample. So yeah, kind of that's maybe another reason to also potentially load multiple ruby spheres. But yeah, so not too big, not too small, maybe on the like 10 micron across.
Okay, so you said that the gasket, steel gasket has a transition.
Yeah.
So what's the safe maximum pressure can you go to steel?
Oh, for steel, I think I wouldn't say you're quite limited by the gasket material itself. I mean, that is kind of going to dictate the failure mechanism, but I can't give you just one number because really it's going to depend on things like how well aligned are your diamonds, are they completely flat and therefore are you compressing evenly but not pinching on one side. So definitely just because things like tungsten are more robust, maybe that might maximize to a higher pressure you could go, but more often than not, it's sort of more just assume, based on the culet size of your diamonds, this is roughly my max target pressure. So maybe for a 600 micron gasket, or culet, I'd go up to maybe 15. For 300 micron, maybe 55 or 60, 200 above that, and so on and so on. So just kind of keep track of what the culet size is for that.
And then
Maybe you can ask after.
Yeah,
Any other
let's chat
questions? Just to cover the rest of the audience. Any other questions?
Are there any kind of good non-metal gaskets or dielectric or something that's non-magnetic?
Yeah, well, so I guess copper beryllium is good for being non-magnetic, right? But I guess maybe, no, not so much. Yeah.
It usually has a cobalt binder.
Oh,
So
okay.
it usually has it's not ordered, but it'll have a signal.
I see. So the cubic boron nitride epoxy matrix is kind of the most kind of customizable way that I've found, but yeah, maybe you're looking for something that you wouldn't also have that underlying steel. I actually, don't have a great sense other than if you find, a non-magnetic steel or something like that. I don't know if anyone else has any other suggestions.
MP35N.
MP35N, okay.
Or nickel chrome aluminum, either one is extremely non-magnetic.
Got it, okay.
Rhenium is
And rhenium.
you just spend it a little more.
Yeah, rhenium's just a little more expensive. Okay, so yeah, just to repeat that, just for sound traveling that way, MP35N was a suggestion, as well as rhenium. And what was the other one? Nickel cobalt alloy.
What is MP35N?
It's made by Carpenter Technology, and you can get it from Hamilton. It's a roller sheet. It's multi-phase 35% The wash down.
Always. That's the mythical.
That's
part of it.
The Russian element. Yeah, that's the nickel chrome aluminum is a Russian element. Very high condensation. And it was reverse engineered by Matsumoto NRIM.
Okay, I'll finish with the most important question. What's the highest pressure you
Oh, I'm not a high pressure chaser, so I've probably only gone up to maybe like 70 something or 80 something.
Okay, it's respectable.
All right.
Is there a unit? There's a bar or
Yeah. Oh, yeah.
GPA. That's not
Yeah. Race is on.
Yeah.
No, I'm certainly not a metallic hydrogen chaser or anything like that.
Okay, thank you very much. Okay, we're running a little late, so we'll start at 11:15. So you have half an hour. There's coffee outside. Save me a cup, please.
Is this similar to the charter?
Oh yeah.
So to get,
Can we draw this?
this is the,
That's great.
give you one number. One number. To get to the same volume, I do 800 microns.
No,
The hardness 55.2, it's